Hello everyone, Mr. Keister here with you again today. This is the video for Wednesday, August the 26th, which is our scheduled fifth day of school for the fall semester. Always keep in mind though that the dates can change for a variety of reasons. Of course, number one being COVID-19, and if we have any alterations to our schedule again due to that. But regardless of that, the lessons will remain the same. Okay, so let's look at today's do nows, which is our schedule for today. Now, today is our scheduled first day of e-learning that was already on our school calendar. So we will not be in class today, at least that I'm aware of as of the time of this taping, and you will be at home doing your e-learning. So let's talk about what's on the agenda for today for you guys at home. You will have picked up page 14, which is, we're going to go over that a little later during this video. I would have handed that out to you yesterday so that you already have it in hand. Today during e-learning, you have 2 quizzes to take. Remember, in Canvas, your lab safety and lab equipment quiz. I hope you've been studying those and are ready to take them. Next, we'll quickly discuss the results of lab activity 1-1 Matter, Part A, which we completed yesterday. And we talked some about the data yesterday and about the particle diagrams. We'll kind of follow up with that and finish that up. And then today's lesson, we'll go over the mass and volume measurement recording handout, which is page 14. And then I'm going to have you try the practice problems for tomorrow. We'll go over that first thing on tomorrow. Also, I have scheduled, as promised, your first online homework assignment in Mastering Chemistry, which is the Introduction to Mastering Chemistry assignment. That is due this coming Monday by 7:30 a.m. It's to be done in your own time and will be shut off at 7:30 a.m. All right, so there's no late policy with Mastering Chemistry. I usually schedule them anywhere from 3, 4, or 5 days out. You have that much time to work on it, and so I don't accept any late work with Mastering. Once that 7:30 on Monday time passes, whatever score you have accumulated is what you get. Okay. If you ever want help in Mastering, you can always skip those problems and shoot me an email or ask me if we're here in person. You can quit working in Mastering anytime. It will go back to where you left off when you return to it. Also, just FYI, you can access your online textbook, your e-text, on your Mastering Chemistry homepage as well. Now, I will have sent you or given you personally the instructions for getting registered in Mastering Chemistry prior to this date. So you should be at this time ready to go with that. Okay, so I think that takes care of our schedule for today. So let me switch the board out here, and we'll first talk about some finishing up work with lab activity 1-1A. So excuse me 1 second. And there we go. So here is our paper from Lab 1-1A, or Lab Activity 1-1A. Now, just as a quick review, remember all of this here was your group's data. Remember also that we compiled a list of class data on the backboard yesterday in doing the lab. And so the in this column here was the class average data, which would go right here. Okay. We also talked about physical and chemical changes, which was part of your notes, your first assignment from your notes packet. And we had predetermined or talked about yesterday The first one, pulling apart steel wool, was a physical change. Burning is a chemical change. Melting, which is just a change in state of matter, is a physical change. Forming a precipitate, chemical. Dissolving sugar, physical. And dissolving Alka-Seltzer, although partially physical, is in reality a chemical change. Remember, the key difference between a physical and chemical change is the identity of the substance. The identity, because the substance's appearance can change without its identity changing. So the key thing is there, did the substance's identity change or did it not? Let me advance this. And yesterday, at the end of the lab activity, I talked about briefly particle diagrams and how to go about drawing those. Now, particle diagrams are to be done very simply. All right. Now, we're going to learn more about them here in the coming days, where we're going to be a little more specific on how we draw them. But the general rule for particle diagrams is don't go crazy. You don't need lots of particles to represent something at the particle level. It can usually be done with a very few. Okay. I believe we did 1, 2, and 3 yesterday. So, and I asked you to do 4, 5, and 6 for today. So let's briefly talk about those. In number 4, forming a precipitate. Here in the before box, again, I have 2 things because we started out with 2 separate substances. Remember, we had 2 solutions. And so if I designate the one solution with colored circles and the other solution with open ones, in the formation of a precipitate, we had a, remember, they combined together in some way and formed a cloudy white or milky white colored solid particle. So that's definitely a change in identity from the original colorless solution. And so again, very similarly to burning steel wool, these combine in some form or fashion. We're not exactly sure how at this time. We will eventually. But just showing that. And the other key thing in a particle diagram is always making sure that the conservation of mass is applied. So here we have 1, 2, 3, 4 particles total as we do here, okay, composed of the same original substances, 2 and 2. Okay, number 5, dissolving sugar. So in this sugar, here again, we have 2 different substances, and I'll just do the same thing. Again, I'm trying to keep it simple here. So we have sugar particles here, and we have water particles here. All right, now, when you dissolve sugar, does the sugar react chemically? And we said, no, it doesn't. When you dissolve sugar in water, what do you get? Well, you get sugar water, right? It's a solution. It's a mixture, physical mixture of the 2 substances that are now in a single phase of matter, in this case, the liquid phase. But we call that a solution. Okay, a liquid is actually pure. I think I mentioned this yesterday. Anyway, so they are not chemically combined as they are or as they were in these 2. So all I'm going to do is show them together, of course, in one container, and I'm just doing this kind of randomly, and so there you have it. Okay, they are both have retained their original identities as individual particles, but now they are somewhat mushed together. Okay. And then the last one. This was the unique one, dissolving Alka-Seltzer or denture cleaner or whatever it was. I'm going to use a couple more particles with this particular one. So we started off with the Alka-Seltzer or denture cleaner particles, which was solid. We started off then with also with water. So if I do and stick with my circles, of course, you can use X's, boxes, triangles. I don't care what you use. I'm going to go ahead and do 3, though, this time. So we got 1, 2, 3 Alka-Seltzer and 1, 2, 3 water. Now, what happened? Okay, so the Alka-Seltzer dissolved, obviously, but it didn't just dissolve. If it had just dissolved, it'd have been a physical change. But it also produced a gas. I think we identified the gas as carbon dioxide gas. This is actually why you take Alka-Seltzer. You drink it, and what do you start doing? Well, then you start burping. Well, that's to release the excess gas in your stomach, which then relieves your stomach ache or heartburn or whatever. That's the purpose of the whole thing. So anyway, because it's that gas buildup that causes you the discomfort. Okay, so we got the production of a gas, which is a completely new substance. However, we still have water particles and probably some Alka-Seltzer particles in this solution as well. So what I did here was kind of similar to here. I'm going to say I still got a couple of each of these particles. The original water particles and the Alka-Seltzer particles. But now, in addition to that, I'll put these up top because gases are not very dense, and of course they rise up. I'm going to put two particles, I'll label them as X's there, and that would be our gas particles. So here's our new substance here. The X is the gas that was formed from the chemical change between these two. So, but if you look all together, we got 3 and 3 is 6 particles there, 6 there. Conservation of mass is followed. Okay? And then the last thing with this activity was to state the law of conservation of mass in your own words. Okay, so there, of course, is a book definition. I gave a definition for you in your notes packet. I asked you to state it in your own words. There's several ways you could have done that. Basically, what it boils down to, and this again, this is just my own wording. You don't have to, yours doesn't have to match exactly. I said that the total mass of a system stays the same both before and after a change occurs. You could also say the total mass of everything before a change equals the total mass of everything after a change, or something similar. Bottom line is this: whether the change is physical or chemical, the conservation of mass applies. Matter is not created during a change. Matter is not destroyed during a change. It just rearranges itself in some way. Okay? So, and your data really, to within reasonable error, prove that in each and every activity that you did. Okay? So that kind of brings us to a close with this particular activity. I will have this posted on the board here in class just to make sure that you got everything down you needed to. I will also have it posted in Canvas so that you can see that from home as well. I did not collect this one for a grade, and as I mentioned in my introductory video, I don't collect everything for a grade, but believe me, everything we do is important. All right. All my test questions and all that stuff comes from the material that is presented or that you do in class, whether I collect it for a grade or not. Always remember that. Okay. All right. So that brings that to a close. We will move on then to our next thing on the agenda for today, and that is beginning to talk about reporting measurements. So let me change the board up here. And this then is page 14, which is today's paper. So I want to talk about two different types of reporting measurements. One, and I mentioned this before, One involves a measuring device that's electronic or digital, and one involves manual devices. All right. So we're going to start with measuring mass, which is done with an electronic balance. I have one right here. Okay. Since this is an electronic device, the precision level or the number of decimal places is already known. All right. Always check to make, and this is a reminder from the other day, always check to make sure that the units are in grams before making your measurements. We only use metric units in this class, or in virtually all science classes. If the units are not grams, let me know, and I will get the thing adjusted for you. Always press the on or tear button for weighing something so that it reads 0.00 grams. If you're weighing solid particles or a liquid, then you'll need a container of some type. We talked about that. You can place the container on the balance first, press the on or tear button to set it to 0, then place the solid substance or object or the liquid in the container, and it will then only weigh that particular substance or liquid. Otherwise, you'd have to weigh the container empty, weigh the combined mass of the container and the substance or liquid, and then subtract the two. Either way works, but with an electronic device, that first way saves you some time. And thirdly, never weigh a solid chemical directly on the metal plate. All right? In other words, never set a solid directly on this metal plate because it could react. Instead, always place the solid chemical on a weighing paper, a little plastic container or weigh boat, a beaker, or something else. Immediately clean up any spills on the balance, whether they be solid or liquid. We also, like I said, this one, and I'm just going to go ahead and hit the on button. I'll go ahead and put a graduated cylinder on there, and it says 147.97 grams. It's already recorded to 2 decimals. That's what you write down. All right. Now, if by chance, and again, it could flip back and forth, meaning the actual mass goes out additional decimal places, but this unit only goes out 2. That's all I can tell you. So your task then is to pick one of the numbers that it reads. Whichever one it looks to appear to be there most often, that's the one I would pick. Otherwise, you just pick one. 1 point, though. If this by chance it said 148.00, okay, 148.00. That's what you record. You don't record 148. You don't record 148.0. Since this device goes out 2 decimal places, even if they're zeros, that's what you record. All right? Always remember that. We also have another digital device that we use fairly regularly, and that is our digital thermometer. Our particular thermometers go out 1 decimal place. So again, this one says it's 23.0 degrees Celsius in this room, which seems about right. Which is give or take around 70 or so Fahrenheit, 72. But anyway, here again, 1 decimal place on that thermometer, that's what you record. So even if it said 20, like I said, if it says 23.0, you don't record 23. You record 23.0. Okay? All right. Now, let's talk about measuring liquid volume. We use a graduated cylinder for that, and a graduated cylinder is a manual device. All right? It's a manual device. Because graduated cylinders have the most divisions or markings, they're called graduations, since that's where the name comes from. They allow for the most accurate and precise liquid volume measurement. We do not use, and I mentioned this earlier, we do not use beakers or Erlenmeyer flasks or anything like that to measure actual volume. Now, you can use those to approximate volume. If it says you need approximately 20 mLs of this, you can use a beaker, all right? But if we need a specific volume, we're using a graduated cylinder, okay? Usually a 10 ml, 25 ml, 50 ml, or 100 ml graduated cylinder is used to measure volume. When you measure the volume of a liquid, always read the liquid level from the bottom of the meniscus. I mentioned this earlier too. Meniscus is the curve that is formed because water is attracted to the sides of the graduated cylinder. That's due to intermolecular forces. All right. And it's also being pulled down in the middle by the other water molecules. So in a graduated cylinder, you're always going to see the liquid, whether it be water or some other liquid, form a curved surface like that. And you read from the bottom of the curve, the bottom. Okay. So since a graduated cylinder is a manual device, you must determine the precision level or number of decimal places yourself. Okay? Here's our first big lesson in regard to measuring, and it is a big one. Believe me. Let me advance the paper real quick. The rule for manual devices is that you record measurements one place further out than the value of the smallest marking on the device. All right? One place further out than the smallest value of the marking device. For example, if the smallest marking is the tens place, all right? So you have markings that say 0, 10, 20, 30, 40, 50, all right? Then you record the measurement one spot further, which would be the ones place, all right? If the smallest marking is the ones place, then you record the measurements to the tenths place, or 1 decimal. If the smallest marking is the tenths, then you record the measurement to the hundredths place, or 2 decimals. Thus, the last digit in your measurement is estimated. On an electronic device, that last digit that reads is estimated too, and you know that by seeing it flip back and forth. All right. Doesn't mean the digit is not valid. It just means that it's estimated. Okay. If the meniscus is on a line and the measurement requires a decimal point, then the last digit would be a 0. So in other words, if this is on 50, all right, 50, and the smallest marking is the ones place, all right, then that means you have to record that out one more spot to the tenths place. So you can't record 50. You record 50.0, all right? That's critical, okay? If the meniscus is between two lines, then estimate how far after the decimal point the meniscus is and record the appropriate number as the estimated last digit. Sorry, my phone went off. Gosh, I hate it when that happens. Excuse me just a minute, folks. Very sorry about that. I'm not in the groove of school yet, and I keep forgetting to turn my ringer off. So I do stupid stuff like that all the time. So don't pay any attention to it. All right. Okay. So one last time. If the meniscus is on a line and the measurement requires a decimal point, then the last digit is a 0. Okay. If the meniscus is between two lines, then estimate how far after the decimal point the meniscus is and record that appropriate number as the estimated last digit. If it looks like it's halfway in between two lines, then that last digit would be a 5. If you think it's closer to one than the other, then maybe you put a 3 or a 7 or an 8. It doesn't matter, whatever you think. All right, whatever you think. All right, so let's look at these two here. Here we have a 50 ml graduated cylinder. All right. If you look here, you can see that the numbered graduations are by 10, but there are 10 markings in between each of those. So that means that the smallest marking has a value of 1 ml. All right. That means then that you round to the 0.1 ml or 1 decimal place. All right. Hence, according to this person that read this, they recorded 43.0 mLs, not 43, even though the meniscus appears to be right on that 3 line. All right, the fact that you must round another space out requires that 0 be there. Okay. Now over here, we have a 10 ml graduated cylinder. And if you see here, the markings, the smallest markings that are marked are the 1 to the whole number. We have a 9 here and a 10 here. But we have 10 markings in between those ones that are labeled. And so there again, based on that, our smallest marking this time is to the 0.1 ml or 1 decimal place, which then means, according to our rule, that we are going to round one place further than that. So we are going to round then to the 0.01 ml or 2 decimal places. And thus, based upon what this person thought here, 9.75 mLs. All right. And he might have said 9.78. He might have said 9.80. Depends on how you're looking at it. Either way, 2 decimal places, because that's what the device tells you to do. All right. That's what the device tells you to do. Same thing is true. Now I used a graduated cylinder here as an example of a manual device. Let me advance the paper to the next page there. The same thing is true of a ruler. All right. So a ruler is a manual device as well. Got one right here. By the way, our rulers have centimeters on one side and inches on the other, but I have actually taped the inches off because here again, English measurements in this class are out, metric only. All right. So the same rule applies with a ruler that does to a graduated cylinder. Whatever the value, you need to determine what the value is of the smallest marking on this ruler. Once you do, you will round a measurement taken with that ruler one place further out. Okay? Measuring solid volume. How does the solid have a regular or irregular shape? That's the key here. How you measure a solid depends on whether its shape is regular, meaning measurable, or irregular, meaning it's not. If the solid has a regular shape, square, rectangle, triangle, cylinder, etc., then its dimensions can be measured with a ruler, and its volume can be calculated using a geometry equation of some sort. If the solid has an irregular shape, though, then its volume must be determined by water displacement. I'm sure you've probably done this before. As in measuring liquids, a graduated cylinder would be used for this. You would measure a predetermined volume of water, make sure it's deep enough to completely submerge the solid. Also make sure the graduated cylinder is large enough to hold that solid. Then carefully add the solid to the water. Just don't want to plunk it in there. A lot of times water will splash out, or you could actually break the graduated cylinder if it's a very dense object. You don't want to do that. So carefully add the solid to the water and then measure the volume again with the solid and water combined. And then you can subtract the 2 volumes, and that'll give you the volume of your solid. Okay. Now, as far as measuring length, which would fall under this regular scenario up here, we use a metric ruler. So again, this is basically what we're looking at right here. There are 10 lines or markings between each centimeter marking. Notice that our markings that are labeled are 1 centimeter, as they are on our actual rulers. However, with there being 10 markings in between those, that means the value of the smallest marking is again goes out to the 0.1 or 1 decimal place. So the smallest marking here is to the 0.1 or 1 decimal place. All right, which then means what? Hopefully you got this now. How are we going to round it? One place further, which would be to the 0.01 centimeters in this case, or 2 decimal places. I probably see more mistakes in regard to measuring with rulers than anything else because people forget this rule, all right? So they measure something here, and it's right on let's say they measure a dimension of something, and it's right there, smack dab on the 1. What do they instinctively write? 1 centimeter. Wrong, all right? 1.0 centimeters in this case. Wrong, all right? It needs to go out 2 decimal places or the hundredths place. The correct measurement would be 1.00 centimeters. All right, got to remember that. Got it. Okay. In this particular one, here's the 2. So here's our object. It goes past 2.3, but does not hit 2.4. Again, based on the fact that it needs to go out 2 decimal places. This particular person measured it, said, well, it's not halfway between, so he doesn't think it's 2.50, so instead, or 2.35, I should say, sorry, 2.35. He thinks it's a little closer to the 0.3 than it is to the 0.4, so they said 2.33 centimeters, which is fine. And somebody else might have said 2.34, somebody else might have said 2.32, whatever, right? Whatever you got, that's what you got. If you rounded it correctly and it appears to be accurate based on the measurement, it's fine by me. Right? It's fine by me. Measuring is very subjective. Okay. All right. Any questions on that? Seems kind of, what's so important about this? Well, I can't stress how important enough that is because chemistry is a physical science. And I mentioned this before. We measure tons of stuff, all right? And then we do math calculations, chemistry calculations based on those measurements. If our numbers aren't recorded properly, then everything we do with those numbers after that, basically, for lack of another term, goes to crap, all right? So, gotta start with this right here, okay? Lastly, in science, we want to make accurate, precise measurements. I'm going to talk more about accuracy and precision a little later on in this unit. In fact, I'm going to probably spend an entire day on it. Measurements that are accurate are close to the true or actual value of what's being measured. All right. So, if the width of this desk is 2.50 meters, all right, that's its true length, okay, or width. Then whatever you measure, how close you are to 2.50, its true value, is a measure of accuracy. All right, that's a measure of accuracy. How close you get to what you're supposed to get. If you measure the same thing several times and get numbers that are close to one another, you have good precision. So let's say we have 6 different groups measure the desk. One gets 2.50, which is right on the money. Somebody gets 2.48, somebody gets 2.44, somebody gets 2.52. They're all very close to 2.50, but now instead of comparing each group's measurement to what it's supposed to be, you're comparing each group's measurement to the average of everyone's. That's a measure of precision. Okay. Precise is how close you get to the average of everyone. Accurate is how close you get to what you're supposed to get. That's the basic difference. Okay. Every measurement has some degree of uncertainty. All right. Even the digital measuring devices, they can't tell you exactly what the measurement is. All right. When you measure manually, of course, it's subjective. All right. So there's uncertainty in every measurement. This uncertainty or margin of error is the result of the last decimal place that we estimated. All right. Is it directly on the line or is it between 2 lines? You are estimating that last digit, as is a digital device. It's estimating the last digit. The more lines or divisions an instrument has, the more digits you know for certain. Okay? Therefore, the instrument is more precise. So a device that goes out one decimal place is more precise than a device that only goes out to the ones place or the tens place. The more decimal places you go out, a device goes out, the more precise the measurement it can give you. Okay, the more precise the measurement. Okay, well, let's go to the next page. And this is where I'm going to stop talking over this. Here are the practice problems I mentioned in today's agenda, today's schedule. So what I'd like you to do is today at home, do this little practice here. I gave you 5 measuring devices and showed you where the measurement is located. Here's the graduated cylinder, of course. And so what I'm asking you to do is 3 things. Number 1, identify the smallest marking on that device. What is its value? Is it the ones place, the tens place, the hundreds place, the thousands place, or the tenths, hundredths, or thousands, whatever? Based on the value of that smallest marking, how would you round? Remember, it's 1 place further out than the value of the smallest marking. And then finally, based on this, look and see what the device measurement is, and you record it to your best guess. Okay? So I'm going to have you do that. It's a very short assignment. Don't forget about your quizzes in Canvas. Don't forget about Mastering Chemistry. And as far as I know, I will see you in class tomorrow. So this is Mr. Keister signing off. Everybody stay safe, take care, and we will see you soon. So long, everybody.